In the vast silence of the cosmos, where stars whisper secrets across light years, we find ourselves drawn to the edge of human ambition, gazing toward a red world that has haunted our dreams since ancient eyes first traced its crimson path across the night sky. Imagine a colossal vessel forged from the fires of innovation, hurling itself against the unyielding grip of gravity, its engines roaring like the birth cries of new suns. This is no mere machine. It is a bridge between worlds, a testament to our restless spirit. Yet, in this dance of metal and flame, a profound mystery unfolds. How does one creation, born from the audacious vision of a single mind, stand against the titans of established might, each vying to claim the dusty plains of Mars as humanity's next frontier? We ponder the invisible forces at play, the raw power that propels us upward, the burdens we carry into the void, and the scorching trials of return, elements that could redefine our place among the stars. It begins with a ship that promises to rewrite the rules, a behemoth known as Starship, evolving through iterations like a living entity, its ninth form a pinnacle of engineering poetry. But what hidden paradoxes lie in its comparisons to rivals, where thrust battles wait, payloads defy limits, and heat becomes a forge of survival? As we embark on this journey, we must ask ourselves, in the grand theater of the universe, what does it truly mean to conquer the red horizon? Picture the solar system as an ancient arena where planets orbit like gladiators in eternal motion. And Earth, our blue cradle, spins with the quiet urgency of a world awakening to its cosmic neighbors. Mars, that enigmatic wanderer, hangs in the void some 140 million miles away on average. Its thin atmosphere, a veil of carbon dioxide whispering winds that carve canyons deeper than any on our planet. The journey there is no gentle sail. It demands vessels capable of escaping Earth's possessive pull, traversing the abyssal gulf, and descending upon a surface scarred by eons of isolation. This is the stage for humanity's boldest gamble, reusable rockets that could ferry us not just to visit, but to inhabit, to terraform, and to transform Mars into a second home. At the heart of this drama stands SpaceX's Starship, a stainless steel colossus towering over 120 meters tall when stacked with its super heavy booster, designed to be fully reusable, a phoenix rising from its own flames. Its competitors loom large: NASA's Space Launch System, or SLS, a behemoth born from the legacy of the Space Shuttle, standing as a symbol of governmental prowess, and Blue Origin's New Glenn, a sleek contender from Jeff Bezos' vision, promising heavy lift capabilities with a nod to reusability. These are not mere rockets, they are embodiments of philosophies, where Starship's rapid iteration contrasts with SLS's methodical evolution and New Glenn's patient precision. Consider the scales. Starship aims for a thrust-to-weight ratio that defies convention, its cluster of Raptor engines generating over 7,500 tons of force at liftoff, propelling a structure that weighs millions of kilograms, yet dances with the agility of a much lighter craft. In comparison, SLS, with its 4 RS-25 engines and twin solid rocket boosters, unleashes about 4,000 tons of thrust, but its expendable nature burdens it with the weight of one-way journeys. New Glenn, powered by 7 BE-4 engines, targets around 3,800 tons of thrust, striving for partial reusability that could bridge the gap. Yet it's in the payload capacities exceeding 100 tons where the true spectacle unfolds. Starship's promise of hauling up to 150 tons to low Earth orbit in its reusable form, dwarfing SLS's 95 tons to the moon, or New Glenn's projected 45 tons. These figures are not abstract. They represent the cargo of dreams, habitats, rovers, life support systems that could seed human colonies on Mars. And then there's the crucible of re-entry, where atmospheric friction turns hulls into glowing embers, testing materials that must withstand temperatures soaring past 1,600 degrees Celsius. Starship's heat shield, a mosaic of hexagonal tiles made from advanced ceramics, is engineered to ablate and regenerate, while SLS relies on proven ablative materials from Apollo eras, and New Glenn experiments with reusable thermal protection. In this expansive vista, we see not just machines but mirrors of human ingenuity, each reflecting a path to Mars dominance. The red planet itself adds layers of reverence. Its Olympus Mons, a volcano thrice the height of Everest, its Valles Marineris rift stretching like a scar from ancient cataclysms, and its polar ice caps holding frozen whispers of water that could sustain life. As we delve deeper, the emotional pull intensifies. These rockets are our extensions, fragile yet defiant, carrying the weight of generations' hopes into the unforgiving black. Beneath the visible spectacle of launches, where plumes of fire illuminate the dawn, lie the hidden signals that reveal the true prowess of these cosmic chariots. Instruments across the globe capture data streams, telemetry from accelerometers charting the surge of acceleration, spectrometers analyzing exhaust plumes for efficiency, and thermal cameras mapping the inferno of re-entry. These are the unseen pulses, the electromagnetic whispers that engineers decode like ancient scribes unraveling scrolls. For Starship, thrust-to-weight ratios emerge from vibration sensors embedded in its Raptor engines, each producing up to 230 tons of thrust, allowing the vehicle to achieve a ratio exceeding 1.5 at liftoff, meaning it accelerates upward with a grace that belies its mass. This is detected not by human eyes, but by ground-based radar tracking the ascent curve, revealing how Starship's lightweight stainless steel body, at just 4 millimeters thick in places, minimizes drag while maximizing power. Contrast this with SLS, where load cells on its core stage measure a thrust-to-weight hovering around 1.2, its massive orange tank, derived from shuttle heritage, adding inertial bulk that instruments quantify through strain gauges, showing how its solid boosters provide an initial burst but fade, leaving the upper stages to labor. New Glenn signals come from similar arrays, with its methane-fueled BE-4 engines promising a ratio near 1.3, captured via high-frequency pressure transducers that map combustion stability, hinting at reusability without the full commitment of Starship. Payload capacities over 100 tons are inferred from orbital mechanics simulations, where GPS satellites track insertion velocities. Starship's ability to loft 100 or 150 tons reusably stems from its Methalox propulsion, efficient in vacuum, while SLS's 130-ton initial lift to orbit is expendable. Its hydrogen-oxygen engines optimized for deep space, but detected as less flexible through fuel consumption logs. Re-entry heat management unveils its secrets in infrared imagery from chase planes, showing Starship's tiles dissipating heat through phase change materials, enduring peaks of 2,700 degrees Fahrenheit, far beyond what naked eyes perceive. SLS's Orion capsule, with its Avcoat ablative shield, sheds layers in a controlled burn, monitored by thermocouples that record temperature gradients, ensuring survival but at the cost of refurbishment. New Glenn's fairing and potential crew modules experiment with reusable composites, their performance gauged by hypersonic wind tunnel data extrapolated to real flights. These hidden signals build a tapestry of intrigue, each anomaly, a slight vibration, a thermal spike, unlocking deeper understanding, as if the universe itself is sending coded messages through the ether, urging us to push boundaries for Mars. In this shared voyage through the stars, we feel the quiet pull of connection, a warmth that bridges the cold expanse. Like wanderers gazing at the same distant light, our hearts align in wonder, reflecting on how these mechanical marvels echo our own fragile quests for a meaning. Let us journey back to the primordial forge, where the seeds of these rockets were sown in the fiery crucible of human curiosity and elemental forces. It begins in the aftermath of the Big Bang, some 13.8 billion years ago, when the universe cooled from its incandescent birth, birthing hydrogen and helium that would fuel the stars, and eventually our engines. On Earth, eons passed as tectonic plates shifted, volcanoes erupted, and metals like iron and nickel coalesced in the planet's core, materials that would one day form the skeletons of our spacecraft. The story of Starship traces to Elon Musk's vision in the early 2000s, but its roots delve deeper, to the chemical alchemy of methalox, methane, and liquid oxygen, elements born in stellar nurseries, where carbon from supernova fused into the building blocks of life and fuel. Imagine the slow emergence. In 2012, SpaceX began developing the Raptor engine, iterating through prototypes in the dusty plains of Texas, each test firing an echo of ancient stellar collapses, compressing fuel with turbopumps that mimic the gravitational squeezes of neutron stars. Thrust-to-weight ratios evolved from these origins as engineers drew on aerospace legacies like the F-1 engines of Saturn V, refining alloys to withstand pressures exceeding 300 bar, allowing Starship to achieve efficiencies where every kilogram saved amplifies power. NASA's SLS harks back even further to the 1960s Apollo program, where the RS-25 engines were first conceived amid the Cold War's fervor. Their hydrogen fuel drawn from water's ancient molecules split through electrolysis powered by solar energy that traces to the sun's fusion core, a process ignited 4.6 billion years ago. Payload capacities over 100 tons emerged from this lineage, with SLS's core stage, a colossal cylinder 65 meters long, forged from aluminum lithium alloys mined from Earth's crust, remnants of asteroid impacts that peppered our world during the late heavy bombardment. Blue Origin's New Glenn draws from a similar elemental wellspring, its BE-4 engines burning methane synthesized from natural gas deposits laid down in prehistoric seas. Their reusability inspired by the cyclical nature of planetary atmospheres, where gases recycle through eons. Re-entry heat management, too, has ancient echoes in the meteors that streak through primordial skies, ablating in fiery trails, teaching us about thermal protection. Starship's tiles, composed of silica and alumina fibers, mimic the resilient crusts of volcanic rocks formed in Earth's mantle, while SLS's ablatives derive from phenolic resins, organic compounds evolved from carbon-rich asteroids. As these systems formed, order arose from chaos. Iterative designs in the wind tunnels simulated atmospheric entries, computational models predicted thrust vectors, and materials science bridged the gap from dusty origins to sleek forms. In this nostalgic reverie, we see the passage of time as a river, carrying dust from cosmic births to the launch pads of today, where Starship 9, an advanced iteration with optimized Raptors and reinforced heat shields, stands as a culmination, ready to propel us toward Mars with the weight of history in its veins. The red planet itself shares this elemental tale. Its basaltic plains forged in volcanic fires 3.5 billion years ago. Its water ice a frozen memory of wetter epochs, inviting us to extend our origins across the void. Science, in its essence, is the art of unraveling memories etched into the fabric of reality, preserving the echoes of launches long past and simulations yet to come. We peer into data archives from test flights, where oscilloscopes captured the rhythmic pulses of engine ignitions, revealing how Starship's thrust-to-weight surged in its Boca Chica trials, each iteration a chapter in a grand chronicle. Fossils of innovation lie in wind tunnel logs, where scale models endured simulated Martian entries, their surfaces scarred like ancient stones, teaching us about heat flux. Particles from exhaust plumes, analyzed in mass spectrometers, whisper of combustion efficiencies that enable payloads beyond 100 tons, while orbital telemetry from precursor missions like Falcon 9 archives the gravitational dances that inform re-entry paths. The voices of discovery resonate through the halls of human endeavor, from the engineers at SpaceX's Hawthorne headquarters to NASA's Marshall Space Flight Center, where timelines of progress unfold. In 2023, Starship's Orbital Flight Test 2 showcased its 33 Raptor engines firing in unison, a feat documented by the James Webb Space Telescope's infrared eyes indirectly aiding in atmospheric studies. Researchers like Dr. Philip Metzger, a planetary scientist, have peer-reviewed papers highlighting Starship's potential for Mars cargo, contrasting with SLS's Artemis ephemeral mission in 2022, which lofted 86 tons to lunar orbit using its interim cryogenic propulsion stage. Blue Origin's New Glenn, slated for debut in 2024, builds on BE-4 tests at West Texas sites, with collaborations from United Launch Alliance underscoring its thrust capabilities. These missions, grounded in rigorous data from the Hubble and ground arrays, paint a picture of competition driving innovation toward Martian horizons. Delve now into the invisible landscapes that underpin these giants, the quantum dances within engine nozzles, the gravitational fields warping trajectories, and the thermal gradients hidden in hulls. Beneath Starship's skin lies a lattice of cryogenic tanks, where supercooled fuels defy entropy, their densities enabling thrust-to-weight miracles that SLS's foam-insulated tanks approximate, but with greater mass penalties. Dark matter analogies emerge. Just as unseen mass shapes galaxies, unobservable efficiencies in New Glenn's staging allow it to punch above its weight, its fairing concealing payloads that could tip Mars missions. Depth reveals contrasts. Starships of full reusability penetrates the economic veil, reducing costs to mere dollars per kilogram, while SLS's expendable core hides the fiscal gravity of billion-dollar builds. Against the harsh voids of space, resilience blooms in unexpected forms, much like extremophiles thriving in Earth's boiling vents or Antarctic ice. Starship embodies this, its structure enduring G-forces that mimic microbial survival in radiation-blasted regolith, paralleling how tardigrades withstand vacuum. Lessons for Mars colonists facing dust storms and cosmic rays. SLS carries this spirit in its robust design, echoing human endurance through historical missions, while New Glenn's innovations mirror adaptive evolution, promising habitats where life clings tenaciously. Beyond our immediate contenders, refuge worlds beckon: Europa's subsurface ocean, Titan's methane lakes, Enceladus's geysers, all potential havens that rockets like these could unlock. Starship's massive payloads could deploy drills to pierce Europa's ice, revealing biosignatures, while SLS's heavy lift might send orbiters to Titan and New Glenn probes to Enceladus, each expanding our search for life with facts like Europa's 100-kilometer deep seas holding more water than Earth's oceans. In this cosmic tension, awareness sharpens, urging us to reflect on the fragility of our pursuits, where every launch carries the weight of irreplaceable dreams. These mechanical marvels mirror our own scars, where human hubris has etched wounds upon Earth. Deforestation akin to Mars's lost atmosphere, pollution paralleling re-entry's fiery toll. Starship's rapid development echoes industrial revolutions that scarred landscapes, while SLS's governmental backing reflects societal divides, and New Glenn's corporate drive mirrors economic inequalities driving environmental collapse. The unraveling accelerates. Imagine Starship faltering in re-entry, its tiles cracking like fracturing ice shelves, or SLS's boosters depleting like exhausted resources, New Glenn stalling amid funding droughts. Viscerally, we feel the shake of failed tests, the heat of budget cuts, the collapse of timelines that could doom Mars' dreams to dust. Yet hidden stakes lurk. Political maneuvers where NASA's SLS secures jobs in key states, economic rivalries pitting SpaceX against Blue Origin in patent battles, moral quandaries over militarizing space. Global analogies abound. Just as Cold War tensions birthed Apollo, today's competitions could forge or fracture international alliances for Mars. Two paths diverge, one of dystopian delay, where infighting strands us earthbound, Mars a barren relic, the other hopeful, with collaborative thrusts propelling thriving colonies. Our choices, investing wisely, uniting visions, balance the future, reflecting on personal roles in this cosmic fork. In quiet closure, we tie these threads, the poetry of flight resonating with our innermost yearnings for the stars. What echoes from the opening mystery now? In the red glow of Mars, do we not see our own ambitions reflected, fragile yet eternal? Finally, we contemplate legacy. These rockets, like ancient monoliths, will outlast us, their journeys etching human ethics into the cosmos. Survival through cooperation. Lessons from Earth's scars ensuring Mars blooms, a generational light guiding species toward unity.